Hi, this is Miss Barber. The title of this lesson is Limits at Infinity and Infinite Limits. In this lesson, we will examine function behavior as the limit approaches a value that causes the function to approach positive or negative infinity, and function behavior as x approaches plus or minus infinity. Recall, infinity, denoted by the symbol that looks like a sideways 8, is not a number. Instead, it describes behavior. We will continue with the study of asymptotes from this course as prerequisite and use calculus to discuss aspects of asymptotes using limits. Exercise. Find the limit as x approaches 3 of f of x, where f of x is equal to the rational expression 1 divided by the quantity x minus 3. While with the limit we are not concerned with what happens at 3, let's go ahead and observe that for the domain of the function, x cannot be 3 because that'll give us a 0 in the denominator, which makes the evaluation at 3 undefined. However, we are very concerned with values that gets very close to 3 from both sides without actually hitting 3. So let's approach those values, and I'm going to begin with 2.9. That's just 1/10 of a unit away from 3. And from the right of 3, let's begin at 3.1. Again, remember we are approaching 3 from both sides. Let's get continually closer. So we'll pick from the left 2.99, and then finally let's see what happens as we evaluate the function to find the limit from 2.999. Now let's approach 3 from the right. We start with 3.1. I'll choose 3.01 and finally 3.001. That's about as close as you can get to 3 without actually getting to 3. Let's evaluate these values on a calculator. I am using a TI-84 Plus SE. I will use the table feature to compute all of our values. So let's begin with a clean screen, and I'm going to choose y equals so I can input my equation. My equation will be 1 divided by, be sure to put the entire denominator expression in parentheses, so open parentheses, x minus 3, and then close parentheses. To use the table feature, we need to get to that function, so push the second button along the left-hand side of the calculator screen, the second one down, and then press the sequence of buttons that'll get you to table set. So along the very top row, it is the second one from the left. Now, we have a table setup screen. Let's go ahead and say where we start doesn't matter. And delta table, the increments don't matter. The only thing we are concerned with here is how to put the values in, which is independent, and instead of auto, we are going to scroll right and pick ask. Now we enter. And then we want to exit the screen, so push the second button again and the button right next to it, which will let us quit the screen. Now we're going to evaluate using the table, so push the second button and the very last button along the top to get to the table. Now we put in the values for x, and the calculator gives us the output. Let's begin with a 2.9. Press enter, and we get an output of -10. So let's just try from the right side, and I'll do 3.1. Press enter. That's a +10. That's kind of interesting. Now let's move a little bit closer than 2.9 from the left side. So we'll do 2.99, and the output is -100. Boy, it's getting real small real fast. Let's see what happens from the right hand side. I'll put in 3 0.01, and the output is positive 100. Let's just try one more unit closer. So from the left, I'll do 2.999. Press enter. I get negative 1,000. Let's see what happens if we approach 3 even closer from the right, such as 3.001, and that gave us 1,000. Let's transfer these values to our table. Transferring the values from the left end, 2.9 was negative 10. From the right end, 3.1 was positive 10. From the left end, the value we chose was 2.99, and that gave us negative 100. And from the right end at 3.01, we got positive 100. And 2.999 when evaluated in the function 1 over x minus 3, the output was negative 1,000. And from the right side at 3.001, the output is positive 1,000. What we could conclude is that if we're looking at 3 where it's not defined, as you get closer and closer to 3 from the left, the function appears to be going to negative infinity. And as closer and closer you get to 3 from the right, the function appears to be going to positive infinity. So let's look at the graph. When we graph f of x equals 1 over x minus 3, we get the vertical asymptote. This is previous to calculus, a vertical asymptote, which is a vertical line at x equals 3. And that corresponds with x not equaling 3 in the domain. And as we have predicted with the values we computed in the table, the closer you get to 3, the faster the function approaches what looks like negative infinity, and the closer you get to 3 from the right, the faster the function approaches what looks like positive infinity. So let's say this succinctly, stating the problem again. Find the limit as x approaches 3 of f of x, where f of x equals 1 divided by the quantity x minus 3. The limit as x approaches 3 from the left, the function approaches negative infinity, and the limit as x approaches 3 from the right, the function approaches positive infinity. Since the left-hand limit and the right-hand limit are not the same, we then conclude that the limit as x approaches 3 of f of x does not exist. The next example, find the limit as x approaches 3 of f of x, where f of x equals 1 divided by the quantity x minus 3 squared. This is very similar to the example we just completed. The key difference is the squared. When we square any real number, it's always going to be positive if it's not 0. So what happens now is that we look at the limit as x approaches 3 from the left of f of x. In the previous example, it approached negative infinity, but in this example, it approaches positive infinity because we squared it. And the limit as x approaches 3 from the right of f of x, there's no change. Well, the increase is a little bit faster, but it will remain positive. Let's observe that the limit as x approaches 3 from the left and from the right approach positive infinity, so we can conclude now that the limit as x approaches 3, period, that's from both sides, approaches infinity. At the algebra level, Vertical asymptotes are defined as vertical lines at the x values for which the function is undefined. We now define vertical asymptotes in terms of limits at plus or minus infinity. Definition: vertical asymptotes are lines of the form x equals a in which x equals a satisfies one of the following. The limit as x approaches a from the left of f of x is positive infinity, or the limit as x approaches a from the left of f of x equals negative infinity, or the limit as x approaches a from the right of f of x equals positive infinity, or the limit as x approaches a from the right of f of x equals negative infinity. For the functions f of x equals 1 over x minus 3 quantity and f of x equals 1 over x minus 3 quantity squared, the vertical asymptote is x equals 3. So, vertical asymptotes of rational functions. If f of x equals n of x divided by d of x is a rational function with n of x and d of x both polynomials, and n of a not equal to 0 and d of a not equal to 0, then x equals a is a vertical asymptote. Now let's extend that to a calculus concept. Removable discontinuity or hole. For the rational function f of x equals the quantity x minus a times m of x divided by the quantity x minus a times s of x, and m of a does not equal 0 and s of a does not equal 0, a removable discontinuity or a hole occurs when x equals a and the value of the removable discontinuity is the ordered pair a comma f of a. Example: find the vertical asymptotes and points of removable discontinuity or hole of the function r of x equals numerator is the quantity x plus 1 times the quantity x squared minus 16 divided by the denominator, the quantity is x squared minus 2x minus 8. In order to solve this problem, we must first factor completely all factorable quadratics. So let's re-express r of x as, and for the numerator, x plus 1 is a linear factor. X squared minus 16 is a difference of squares, which can be factored to x minus 4, x plus 4, and the denominator, the quadratic x squared minus 2x minus 8, can be factored into two linear factors. One would be x minus 4 times x plus 2. Now, if we did not cancel common terms, we would appear to have two vertical asymptotes. That's at x equals 4 and x plus 2. However, the x minus 4's cancel, and so this simplifies to x plus 1, x plus 4 divided by x plus 2. Now we will see that the vertical asymptote would be the x value at which the function is undefined would be x equals minus 2. Now, the removable discontinuity is first the x value of the canceled terms, and so x minus 4 was canceled, and it would happen then at 4 and the function evaluated at 4. Let's find the actual location, so we will compute r of 4 in the simplified version. So we will have 4 plus 1 times 4 plus 4 divided by the quantity 4 plus 2. So the numerator is 5 times 8 divided by the denominator, which is 6, And that simplifies to 40 over 6, which simplifies even more to 20 over 3. So we can write the location of the removable discontinuity as 4, 20/3. For the function f of x equals the quantity x squared minus 2x divided by the quantity x cubed minus x, find the critical values of f of x. Critical values are the x values in which something critical happens, such as equals 0 or is undefined. So let's begin by first factoring our given function. X squared minus 2x is a common factor of x. We factor that out, and what remains would be x times the quantity x minus 2. Let's look at the denominator. X cubed minus x is a common factor of x. So we can factor out the x, and what remains would be x squared minus 1. X squared minus 1 is a reducible quadratic, so let's write the numerator again as x times x minus 2. And the denominator would be x times, and x squared minus 1 is a difference of squares, so we'll write that as x minus 1 times x plus 1. So where the function equals 0, it appears to happen at, so I'm going to write f is 0 at, and we set the numerator terms equal to 0 when we want the function to be 0. So that would be at x equals 0 and x equals 2. And another critical behavior is when the function is undefined. And one of the places in which a function is undefined is when the denominator equals 0, and that'll happen at x equals 0, x equals 1, x equals negative 1. Those are the three x values for which, when plugged in, the denominator would be 0. I would like to call our attention to the fact that x equals 0 or undefined at a same value in the numerator and denominator. Let's keep that in mind, because this is what gives us a point or points of discontinuity. Let's continue. Part B. Find the asymptotes and removable discontinuities, which we call holes, of f of x. And we recall from the previous work we did that x equals 0 was a critical value for both the numerator, making the function equal 0, and the denominator, causing the function to be undefined. So we will conclude that we have a removable discontinuity at the ordered pair 0, f of 0, where we evaluate f of 0 with the reduced or simplified function. And we have a vertical asymptote where the function is undefined. And that happens at x equals 1 and x equals negative 1. We have vertical asymptotes. We previously considered functions where approaching a specific x value resulted in the function approaching positive or negative infinity. We will now examine function behavior as x approaches positive or negative infinity. Limits of power functions at infinity. Let p be a positive real number and k be any real number except 0. Then 1. The limit as x approaches negative infinity of k divided by x to the power of p equals 0 when x to the p is a real number for negative values of x. 2. The limit as x approaches infinity of k divided by x to the p equals 0 when x to the p is a real number for positive values of x. 3. the limit as x approaches negative infinity of the product of k times x to the power of p equals either negative infinity or positive infinity. The sign of infinity depends on the sign of the product of k and x to the power of p. 4. The limit as x approaches positive infinity of k times x to the power of p equals either negative infinity or positive infinity. The sign of infinity depends on the sign of the product of k and x to the power of p. Example, find the limits. A, the limit as x approaches negative infinity of 5 divided by x cubed. We will use the properties we just learned. X goes to negative infinity, and negative infinity raised to an odd power, or any negative raised to an odd power would be negative. Even so, this would equal 0 because the denominator gets increasingly large, which makes the fraction get closer and closer to 0. Let's do part B. The limit as x approaches positive infinity of negative 7 divided by x to the power of 4. Again, the denominator gets increasingly large, and as the denominator gets increasingly large, the fraction gets closer and closer to 0. Part C, the limit as x approaches negative infinity of 4 times x squared. Now, this is telling us it's going to infinity of sorts. If it's raised to an even power, a negative times negative makes it positive. 4 is a positive number, so the result as limit approaches negative infinity of 4x squared is positive infinity. Just for clarity, let's consider the graph of the parabola of 4 times x squared. What we do know is that the parabola is facing both ways up, so as x gets closer and closer to negative infinity, the graph itself continues to increase. Let's continue. Part D, the limit as x approaches positive infinity of negative 3 times x cubed. So x is approaching positive, raised to an odd power, or even, raised to an odd power will still remain positive, but the constant that's multiplied to it is negative. So this graph will approach negative infinity. And part E, the limit as x approaches negative infinity for 5 divided by x to the power of 3/2. Let's recall x to the 3/2 using root notation is the square root of x cubed. And the square root is undefined, so let's go ahead and indicate which is undefined for negative values of x. Negative values of x. Therefore, this limit is undefined. Horizontal asymptotes. Definition. The line y equals b is a horizontal asymptote if for the function f of x either or both of the following are true. The limit as x approaches infinity of f of x equals b, or limit as x approaches negative infinity of f of x equals b. A horizontal asymptote is used to describe end behavior of a function. Horizontal asymptotes. Let's recall from algebra, for the rational function r of x equals the numerator n of x divided by the denominator d of x, set equal to the numerator as a polynomial a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus ... plus a sub 1x plus a sub naught, and the denominator expressed as a polynomial b sub m times x to the m plus b sub m minus 1 times x to the n minus 1 plus plus b sub 1 times x plus b sub naught for a sub n not equal to 0 and b sub m not equal to 0. 1. If the degree of the numerator is greater than the degree of the denominator, then the function does not have a horizontal asymptote. 2. If the degree of the numerator is less than the degree of the denominator, then the function has a horizontal asymptote of y equals 0, which is the x-axis, and 3. If the degree of the numerator equals the degree of the denominator, then the function has a horizontal asymptote of y equals the ratio of the leading coefficient a sub n divided by the leading coefficient b sub m. Example, find the horizontal asymptotes of the following functions. A, f of x equals the numerator x squared minus 2x divided by the denominator x cubed minus x. Let's observe that the degree of the numerator is less than the degree of the denominator. Therefore, by the rules we have just learned, the horizontal asymptote is the x-axis, y equals 0. B, g of x equals the numerator 2x minus 5 divided by the denominator 3x plus 7. Let's observe that the degree of the numerator and the degree of the denominator are the same. When those degrees are the same, the horizontal asymptote is the ratio of the leading coefficients. So we would have y equals the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 3. Part C, h of x equals the numerator 5x to the fourth minus x cubed minus 4x plus 13, and the denominator x squared minus 2x plus 1. Let's observe that the degree of the numerator is greater than the degree of the denominator. Therefore, we conclude by the rules we have just learned, there is no horizontal asymptote. Now, the calculus approach. The limits of polynomial functions at infinity. Let p be a positive real number and k be any real number except 0. Then, for the polynomial p of x described as a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus plus a sub 1 times x plus a sub 0, where n is a non-negative integer and a sub n does not equal 0, we define 1. The limit as x approaches infinity of p of x equals infinity or negative infinity, and 2. The limit as x approaches negative infinity of p of x equals infinity or negative infinity. The limits represent the end behavior of polynomial functions. And so, for the first one, this describes the right end behavior, since x is approaching positive infinity, and for the second one, this describes the left end behavior, since x is approaching negative infinity. Example, use limits to describe the end behavior of g of x equals 3x to the fifth plus 2x squared minus 7x. It is sufficient to consider the limiting behavior of the leading term only. So, solution for right end behavior. The degree of the leading coefficient is 5, which is odd, and the leading coefficient itself is 3, which is positive. Therefore, the limit as x approaches infinity of g of x equals infinity. Left end behavior. The degree of the leading coefficient is 5, which is odd, and the leading coefficient 3 is positive. Therefore, the limit as x approaches negative infinity of g of x equals negative infinity. That was fun. Let's do another one. Use limits to describe the end behavior of f of x equals negative 4x to the fourth plus 5x minus 10. Again, it is sufficient to consider the limiting behavior of the leading term only. So, solution, right end behavior, that is, as x approaches positive infinity. The degree of the leading coefficient, 4, is even, and the leading coefficient is negative 4, which is negative. Therefore, the limit as x approaches positive infinity of f of x equals negative infinity. And now the left end behavior. The degree of the leading coefficient, 4, is even, and the leading coefficient, negative 4, is less than 0. Therefore, the limit as x approaches negative infinity of the function f of x is equal to negative infinity. An extra example. A refrigerator production company makes a conventional model at the sales price of $900 and an annual energy cost of $68. The company also makes an energy efficient model at the sales price of $950 and annual energy cost of $56. Part A, express the total cost C sub c of x and the average cost C sub c of x with a bar over it equal to the ratio of C sub c of x divided by x of purchasing and operating the conventional model for x years. So let's begin with the total cost, C sub c of x. The initial purchase price of the conventional model is $900, and for each year that you own it, it's going to cost you $68. Now let's compute the average cost, C sub x bar. That is equal to the ratio of C sub x divided by just x. So in the numerator, we will have 900 plus 68x divided by x, and after we simplify, we will get that the average cost of maintaining a conventional model for x years is 900 divided by x plus 68. Part B. Express the total cost C sub e of x and the average cost C sub e of x with a bar over it, which is equal to the ratio of C sub e of x divided by x of purchasing and operating the energy efficient model for x years. Let's begin by finding the total cost, C sub e of x. To purchase an energy efficient model, the price is $950, and for each year you own it, it will cost you $56, so 56 times x. Now let's compute the average cost, which will be the ratio of 950 plus 56x divided by x. Let's do the algebra, and we will get C sub e of x. That's the average cost, because we put a bar over it, of maintaining an energy efficient model over x years, be 950 divided by x plus 56. Part C. Find the limit of each average cost function as x approaches infinity and interpret the implications of the results. So let's first take the limit of the conventional. So the limit as x approaches infinity, and the average cost for the conventional we computed as 900 divided by x plus 68. Using the limit properties, as x gets real big, 900 over x real big is 0. 68 is a constant, so we get 68. So I'll write it as $68, and let's take the limit as x approaches infinity of the conventional model, which we had earlier solved as 950 over x plus the yearly cost of 56. Now, as x gets real big, 950 divided by a huge number and continues to increase will be 0. So what remains is the constant, which is 56. Let's go ahead and write that as 56. And it says, interpret the implications of the results. The implications of the results are, as soon as you get your refrigerator paid off, it will cost about $12 more per year to maintain the conventional model than it does to maintain the actual energy efficient model.